In this video, we're going to be addressing partial pressure. Partial pressure is the pressure of a particular gas in a mixture. So in the previous problems that we did where we had multiple pressures, they told you the pressure of a gas was. And so that was the pressure of that specific one. It's called Dalton's law of partial pressure. This is the same Dalton that we had in chapter 2 with Dalton's atomic theory. Also the color blindness and the fact it runs in families. And basically, it states the sum of the partial pressures of all the different gases in the atmosphere or in the mixture is the total pressure of the mixture. So when we talk about, I said atmosphere is 78% of the nitrogen. So that means that 78% of the atmospheric pressure comes from nitrogen. And so the pressure total, which I normally would put a T here for total, is the pressure of gas A plus the pressure of gas B plus the pressure of gas C for however many gases you have. And so this example here shows that I have 300 kilopascals of the blue gas, 600 kilopascals of the purple gas, and 450 kilopascals of the yellow gas. And when I mix all three of these gases together, the 300 plus the 600 gives me 900. And 900 plus 450 gives me 1350. So the total pressure in my flask is the sum of all three gases together. That's one from the internet. This one's from the textbook that shows you have flask A and flask B. This is something easy to do. This is a liquid. By filling this flask with the liquid, it displaces all the gas over to this one, okay, by opening up the stopcock. And so this is hydrogen and helium. So this one had 152 millimeters of mercury. This had 608 millimeters of mercury of hydrogen. They said oil because oil is not going to dissolve the gas. So they displaced all the gas by adding oil. And my total pressure then becomes 760 millimeters of mercury inside the mixture. So there's something called a mole fraction, which we don't do a whole lot of this semester. We do use it in 1212. And I don't know why this book is very slow. Like it didn't introduce N until we got to molarity, or even when we got to molarity. The mole fraction is symbolized by X, a capital X, sub A. So this would be the mole fraction of A. And you can get it by either taking the moles of A over the moles total, which makes sense for a mole fraction. But it can also be, because there's a relationship between the moles and the pressure, it can also be the pressure of A over the total pressure gives you the mole fraction of A. And we're going to actually use this part of that formula, like I said, in 1212. Okay? So the first problem says it wants me to calculate the total pressure. So PT is equal to what? When I have N of helium is 0.300 moles. I have N of oxygen is 0.0400 moles. I have a volume of 4.0 liters. And I have a temperature of 20 degrees C. Now there's two ways to do this problem. There's the long way and the short way. I'm going to show you the long way first. Okay. So if I have moles, volume, and temperature, that means I'm going to use the ideal gas law. So I need to know that R is 0.0821, which is that constant. Okay. So the long way would be to use the ideal gas law, PV is equal to nRT, for both the helium and the oxygen. So the pressure of helium is the volume over the times the moles of helium, RT. So I'm solving for pressure of helium. The volume is 4.0 liters. The N of helium was 0.300. R, of course, that constant, 0.0821. And temperature has to be in Kelvin, so I add 273 to get 293 K. It always has to be in Kelvin, 293 here. So I get 4.0 pressure. When I multiply this side together, I get 7.217. So my pressure of helium is going to be 7.217 divided by 4.0 to give me 1.80 atmospheres. I'm going to do the same thing for oxygen. I have my pressure of oxygen is times the volume of 4.0 liters. The N of oxygen is 0.04 the moles, and R is 0.0821, and my temperature is still 293 K. So again, this gives me 4.0 PO2. This time the right multiplies out to be 0.9622. So the pressure of oxygen is 0.9622 divided by 4.0, and that gives me 0.2406 atmospheres. So then my pressure total is going to be the pressure of helium plus the pressure of oxygen. So it's going to be 1.80 plus 0.2406 to give me 2.04 atmospheres. Okay, so that was a long way of doing it. All right, there's a much shorter way, and that shorter way involves the fact that I can say that pressure total times volume is N total over RT. Okay, N total is simply my 0.300 for the helium plus 0.0400 moles for the oxygen to give me 0.340 moles. And so my pressure total times the 4.0 is going to be 0.340, same gas constant, 0.0821, times same temperature, 293. So again, I end up with 4.0 PT. And this time the right ends up being, when I multiply it, 8.179. So PT is 8.179 divided by, that is a 9, divided by 4.0. So my pressure total ends up being 2.04 atmospheres. Okay? So it doesn't matter which way you do it. Of course, the blue is much longer because you found the pressure twice. For both of them involve using the ideal gas law and adding. Okay, but this one involved doing the ideal gas law twice and then adding versus adding and then doing the ideal gas law once. It doesn't matter which method you use. Okay, both of them are equivalent, and I don't care which one you do. All right. The next one, okay, says that I have a diving bell of oxygen and helium, and the gas mixture has a pressure of O2 is 0.200 atmospheres. I have a total pressure of 3.0 atmospheres. It wants to know what the mass of helium is. I have a volume of 10.0 liters, and I have a temperature of 40 degrees C. Okay, so again, there's a long way and the short way of doing this. All right, the long way, actually there's 3 different ways of doing this one, but let's do the 2 that I just showed you. Okay, I can find out what the total number of moles are by P total times V is equal to N total RT, because I have a total pressure. So it would be 3.0 times the 10 liters. N total would be what I'm solving for. I didn't put my question mark up there. R, of course, is 0.0821. Temperature has to play plus 273 to give me 313 K. So 313. So 3 times 10 gives me 30. When I multiply the right-hand side, I get 25.70 NT. So 30.0 divided by 25.70 gives me NT. NT is 1.167 moles total. I would need to do the same thing for the oxygen. Okay, so my N of O2 volume, not N of O2, pressure of O2 is now N of O2 RT. So my pressure of oxygen was 0.20. times my volume of 10. N of O2 would be what I'm solving for, times 0.0821 times 313. So 0.2 times 10 gives me 2.0. And this is going to be the same answer here of 25.70 times N of O2. So 2.0 divided by 25.70 gives me N of O2. And so N of O2 is going to be 0.07782 moles. And then I know that N total is going to be my N of O2 plus my N of helium. So I have 1.167 is equal to 0.07782 plus N of helium. 1.167 minus 0.07782 is N of helium. So N of helium is equal to 1.089 moles, okay, of helium. And then to get the mass, I need the molar mass. So the molar mass of helium, which is the same as the atomic mass, is 4.0 grams per mole. So the mass is equal to the moles, 1.089, times the 4.0, gives me 4.36 grams of helium. Okay? And that right there is my answer. Okay? So that's the long way of doing it, where I did, again, the ideal gas law twice to figure that out. Okay? Pause it right now if you're not finished writing, because I'm getting ready to erase the entire ink on the slide. So pause it. Now I'm erasing. All right, well, it's easier to rewrite the little bit that I need, okay, which was the pressure of O2, of O2 was 0.200 atmospheres. The pressure total was 3.00 atmospheres. They want to know what the mass of helium is. I have a volume of 10.0 liters. I have a temperature of 40 degrees C, which plus 273 gives me 313 K. All right, so the short way of doing this is to realize that the partial pressures, the pressure total, is the pressure of O2 plus the pressure of helium. So I have 3.0 is equal to 0.20 plus the pressure of helium. So 3.0 minus 0.20 gives me pressure of helium. So I have 1.80 atmospheres is the pressure of helium. Now that I have the pressure of helium, I can find the moles of helium using the ideal gas law. So the pressure of helium volume is the moles of helium, RT. So I have 1.80 times 10, N is what I don't know, times 0.0821 times 313. So it's going to be 1.80 mole is equal to, again, it's still going to be that 25.70 N of helium. So 1.80 divided by 25.70 is N of helium. So N of helium is equal to 1.089. Again, the molar mass of helium is 4.0 grams per mole. So the mass is equal to 1.089 times 4.0, which gives me the 4.36 grams of helium. Okay? And actually the moles here of helium is the same from the previous way of doing this if you go back and look at your notes. Okay? You can also do it using the formula, but I'm not going to necessarily show you that of using the mole fraction. you could do that from pressure of helium. I guess I can show you that. So we know that the N of helium over N total is the pressure of helium over the pressure total. Going back to the previous where I had erased that, I'm trying to think if this is the way you'd want to do it actually. I don't think so, because you would still have to, you can get the pressure of helium by subtracting, you have the pressure total, but I'd have to do the ideal gas law to get the pressure total. So this is actually still longer than this method here, so I'm not going to show you that. Okay? Alright, in the next video we're going to be talking about using partial pressures with water.